Hey everyone, welcome back for some more set theory. So I got a question for you. Have you ever felt empty on the inside? Have you ever felt like a set with no members? Well, if so, you have something in common with the empty set. So what does that mean exactly? Let's look at an example, the kind of example that we've seen before, and see what happens when we run into a situation where a set has no members in it. So let's have a look.
Okay, so let's look at a new example here. We've got three sets, A, B, C. All of them are intervals over the real number line, and we need to find various kinds of intersections, unions, and complements. So, okay, starting point, let's sketch the number line. Okay, now we have a number line, we can start sketching some of the intervals. So let's start with A, and we'll do it in this orange color. So A, so it starts at 8. It doesn't include 8, so about there. And it goes to 16, and it does include 16. How about B? We'll do that in green. So it starts at 12. It's about there. It doesn't include 12, and then it goes all the way up to 24, which it does include. So actually, we can see all of these intervals, they don't include the left boundary, but they all include the right boundary. So C, it goes from 20 to 44. Okay, so 20 doesn't include 20, but does include 44, about there. Okay, so let's get down to business. Let's get down to business. A union B. Okay, so we remember that union is the total area, while intersection is the overlap, right? Remember that? Okay, so A union B. So it's the total area covered by A and B. So we can see it starts at A, not including the left boundary, because the left boundary of A is not included, and the left boundary of A is 8. And we're using the curved bracket to show that it's not included. And then it goes all the way to the right boundary of B, which is 24. And 24 is included, so we use the square bracket. Okay, easy. Now let's look at the intersection of A and B. So we know that intersection is the overlap. So let's see where A and B overlap. So they overlap from about here to here, right? So, okay, so it starts at 12. Now, here's a big question. Is 12 included? Because 12 is part of the interval A, but it's not part of the interval B. And remember, to be in the intersection, you need to be in both sets. So 12 is not included, even though it is in A. Okay. And then it ends here at 16 at the right boundary of A. Okay, is 16 included? Well, here 16 is included because it's in both B, because right in the smack in the middle of B, and it's the right boundary of A, and it is included. So it'll be 12 to 16 like that. Okay, so that's those two. Let's look at some complements. So what would the complement of A be? The complement of X is the opposite of X. Okay, so the complement of A will be all the points that are not in A. So it will include this point, 8, and it will not include this point 16, because we want to be the reverse of A. If it's included in A, it's not included in the complement, and vice versa. Okay, so this green shaded area would be the complement of A. So we can see it's a discontinuous interval. So where's its left boundary? It just goes all the way to negative infinity. Negative infinity, all the way to 8. And it does include 8. Oops. It does include 8 because 8 is not included in A. Okay, and then we have a second part of the interval, which starts at 16. Not including 16 because 16 is included in A. And then it goes all the way to positive infinity. Okay, so this is a discontinuous interval because it has a gap in the middle of it. So we connect the two parts of the interval with the union operator, right? Because the complement of A is the total area of the interval before A and the interval after A. And because it's the total area, we use the union symbol to connect them up. Okay, let's do the same process with B. So the complement of B, again, it goes all the way up to the left boundary of B, which is 12, including 12, because 12 is not included in B. And then it starts back up again after B is finished. So B finishes at 24. So it starts there, not including 24, because 24 is included in B, and then goes all the way like that. So again, we're starting at negative infinity. One day I'll get good at drawing those infinity signs. Okay, it goes all the way up until the left boundary of B, which is 12, including 12, union, starting at 24 and going all the way to positive infinity. Okay, great. Okay, now we want the union of A and C. Now we can see that A and C, right? A and C, they're discontinuous. So there's a gap in the middle here, right? So it's basically just going to be the union of the intervals A and C. So it goes from 8 to 16. Union the interval C, which goes 20 to 44. Okay, now we get to a more difficult question. We get A intersect B. Now remember that intersection is the overlap, but A and C don't overlap. A and C are actually discontinuous. So what would we write here? So it's the set of numbers, so real numbers, that are, let's say, that are in A and in C. But how could a real number be in A and in C? Because A is between 8 and 16, and C is between 20 and 44. So there's no real number which could be simultaneously in both sets. So we have a special symbol for this kind of set, right? This kind of set where the condition is impossible for any element to meet. And we call that the empty set. So we notate it with this circle with a diagonal line through it, and we call it the empty set. So the empty set is the set with no members, the set where the condition for entry is impossible to meet.
Okay, so what was important there? The empty set is the set with no members in it. It's a set where the condition on entry is impossible to meet. Now, I want to have a look at what it means when the empty set is a subset of another set. What does that mean exactly? Let's have a look.
Let's try and get a handle on the notion of subsets when one of the sets is empty. Okay, so we've got two sets here. A, which is not an empty set, it contains three members, 1, 2, 3, and B. X is a real number and X is greater than 1 and less than -3. Well, again, we know that 1 is to the right of -3 on the number line. So X could never be between 1 and -3. X could never be greater than 1 and less than -3. So B will be empty. Okay, so true or false, is A a subset of B? Let's think about it. Let's think about definition of subset. So we've got set A. So if A was a subset of B, it would mean that A was wholly contained within B, like so. So if A was a subset of B, it would mean all of these three faces, which are in A, they also need to be in B. So we know that that can't possibly be true because B is empty. B has no members in it. So this has to be false. Okay, let's look at B. Is B a subset of A? Now this one is a little trickier. So B is empty and A has 3 members. So, you know, is B really a subset of A? Well, let's think about it. Let's assume, for the sake of argument, that B is not a subset of A. Let's assume that B is not a subset of A. So what would that mean? It would mean we have some set A, and then B has some region which exists outside of A. That's the necessary condition for B not being a subset of A. You know, there's some region, there's some element, there's at least one element which is in B but not in A. If B is not a subset of A, then we have to conclude there is an X in B and X is not in A, right? But automatically we know this cannot be true. So if we make the assumption that B is not a subset of A, we have to conclude there is a X in B and X is not in A, right? We have to satisfy this condition. But we know that this is false because we know there's nothing, there is no X in B. So if we assume B is not a subset of A, we run into a contradiction. This statement, X is in B, there is an X in B. This statement, there is an X in B, we know it is false. It contradicts one of our starting assumptions that B is empty. So this cannot possibly be true, because assuming that B is not a subset of A leads us into a contradiction. We know that it's false that B is not a subset of A, so the opposite must be true, right? We proved the falsity of this statement here. We proved the falsity of this statement, so the opposite of this statement must be true. Okay, so this leads us to a very important conclusion, that the empty set is a subset of every set. So anytime you have this statement, it does not matter what A is. A could be anything. This statement here is always true. If you've got empty set is a subset of, you don't even need to read the rest of it. You already say, boom, we know that's true.
Okay, so the most important takeaway there is that the empty set is a subset of every other set. So no matter what the other set is, the empty set is its subset. Okay, so a question for you. Why is it called the empty set? Why isn't it just a empty set? Are all empty sets the same essentially? So let's have a look at that.
Okay, so let's go back to this original question. Why is it the empty set? So all sets with no members are equivalent. So let's think about this in a bit more detail. We know the definition of A equals B, where we have two equivalent sets. We talked about that in a previous video. When A equals B, when the two sets are equivalent, that means that A is a subset of B and B is a subset of A. So when two sets are subsets of each other, that means that they're equivalent. Okay, so let's say we have two sets. We have A equals and B equals, what should B equal? B equals 1, the set containing 1, minus the set containing 1 and 2. Okay, so we've got two new sets here. A equals the set of real numbers such that they're greater than 10 and less than 5, and B equals the set containing 1 minus the set containing 1 and 2. Okay, so we know that A is empty, right? There are no numbers which are greater than 10 and less than 5. No numbers satisfy this condition. And let's look at B. Well, we know that the definition of difference, all the elements on the left which are not on the right. So we only have one element on the left, we have 1, and it is on the right. So B is also empty. So we know from the previous slide that the empty set is a subset of X for any X. It doesn't matter what X is, X could be any set, the empty set will be a subset of it. Okay, so given that we know A is empty, we know that A is a subset of B. Because A is empty, and the empty set is a subset of every set, we know this is true. Given that we know B is empty, so we know B is empty, right? Because B is this set here. We know B is empty, so B is a subset of any set. So it doesn't matter what the other set is, because B is empty, B is a subset of A. So this is true as well. So given that A is a subset of B and B is a subset of A, we conclude that A and B are equivalent. So what this means is that all sets with no members, all empty sets, all sets with no members are equivalent. That's because any two empty sets are subsets of each other.
Okay, so we've got two really important rules when thinking about the empty set. The first is that the empty set is a subset of every set. The other thing is that all empty sets are equivalent. So if two sets are empty, then they're just the same set. So those are pretty much the only principles you need to know about the empty set. So let's have a look at some more complicated examples to really get a handle on this concept.
Okay, next one, true or false? So let's look at the first one. Is 0 member of the empty set? Well, the empty set contains nothing. So the set containing 0 can never be the empty set, because the empty set has no members, but the set containing 0 has at least 0 in it. So we know that 0 can never be a member of the empty set. So this is false. Okay, B, is the empty set the same as the set containing the empty set? Now, this is something that trips students up a lot. This just goes back to our old axiom that A is not the same thing as the set containing A. Because the empty set is a thing, right? The empty set is a thing. It's a set, right? It's not just nothing, it's a set. It doesn't have any members in it, but it's still a set. So the set containing the empty set is a set that contains something. So here on the left, we've got a set that contains nothing. And here on the right, we've got a set that contains one thing. It contains another set. Now, that set happens to be the empty set, but that's not super important for us. The most important thing is that these two things are not equivalent, just because A is not the same thing as the set containing A. Okay, just on the other hand, the empty set is a member of the set containing the empty set, right? Because this set here, it contains something, it contains the empty set. So this set is a member of it. And what about this last one? Is the empty set a member of the empty set? Well, no, it can't possibly be, right? Because if this set contained the empty set, it wouldn't be empty anymore. It's just the same thing. It's the same deal as A. You can never have X where X is anything is a member of the empty set. This is always false.
Okay, so now we have a little bit more expressive power. We can express some concepts that we couldn't express before. So one thing we can say now is whether A and B overlap or not. So if we want to say that A and B don't overlap, they don't touch, they don't have any region in common, all we can say is just the intersection of A and B is empty. If the intersection is empty, that means they don't touch. And likewise, we can say they do touch. We can say that A and B do have a common region, a bit where they overlap a little bit. If we want to say that, we can just say the intersection of A and B is not empty. So let's have a look at an example where we play around with this concept.
Okay, let's look at something a little more complicated. So this question is asking us to draw a Venn diagram that satisfies the following conditions. Okay, so let me draw this can be our region for our Venn diagram. So this is our universe. Okay, so let's look at the conditions. So A intersect B is empty. Okay, so let's make this one A, and then we'll do a different color for B. Let's do it in blue. We know the intersection of A and B is empty, so they can't have any overlap. So this can be B. Now the intersection is empty, so we've got that one sorted. Now, okay, the next condition. Okay, so we know that A is a subset of C, and then let's look at this, the third condition. So C intersect B is not empty. So C intersect B. So the overlap of C and B is not empty. So that means that C and B overlap a little bit. So C has to totally envelop A. So A has to be totally contained within C, and then C and B have to have a non-empty intersection. So C and B have to overlap a little bit. So let's draw C. So A is totally contained within it. C and B overlap a little bit. So here's C. So we know A is totally contained within C. We can see that visually. And then C and B overlap a little bit. So we've got that one right as well. Let's look at the next one. Okay, so A is a subset of B. So let's do A here. This can be A. And now it's a subset of B, so B has to totally envelop it. Okay, we've got that one right. Now C is a subset of B as well. Now before we draw C, let me just look at this condition. So A intersects B is not empty. Okay, so C is another subset of B. So like A, C is going to be totally contained within B. Let's do a different color for C. And then C and A overlap a little bit. So something like that. Okay, so let's just check it. A is a subset of B, so A is contained within B. C is a subset of B, so C is contained within B. And then A intersects C is not empty, so they overlap a little bit. So that one's good too. Okay, last one. A intersect B is not empty. Okay. Now there's lots of different ways A intersect B could be non-empty. Actually, let's look at it if there's a little more detail here. So, okay, so they intersect, but A is not a subset of B. So let's draw them side by side like this. Okay. So they have a little bit of an intersection. So that's good. Okay, B intersects C is also not empty. So C and B have to overlap as well. Now, we could draw C here, we could draw it here, we could draw it maybe around B or something. But our next one says that A intersects C. The overlap of A and C is empty. So A and C have to be disjoint. They can't touch each other. And then there's one final condition that C is not a subset of B. Okay, so let's just do it here. Okay, so now let's do a little check. So B intersects C is not empty. Yes, we got that right. Because they have a little bit of overlap here. So that's good. A intersects C is empty. That's good because A and C, so the red and the blue circles, they don't touch each other. So their intersection is empty. That's good. A is not a subset of B. Yep. There's at least one element that's outside B but in A. So that's good. And C is not a subset of B. So yes, there's at least one element that's in C but not in B. So that's good too. Okay, so we are done.
Okay, so that's about it for the empty set. I will see you next time, and make sure you let me know in the comments what kind of topics you want me to cover, and make sure you like and subscribe, help support the channel. Thanks so much for watching.